We have to prove now that the group that we introduced in problem 11.2 is isomorphic to the additive group of integers here. And I bring here the problem just to remind you what this group was. It was the group of matrices, this type of matrices, right, where n is an integer there. So it's 1 in the diagonal, n an integer here, and 0 here. I'm going to call this matrix an, for instance. Okay, and the multiplication is the standard matrix multiplication, right? Well, it's very easy to find a mapping from this to this group here. The mapping is just this. Let me call this group G, right? But G with matrix product. Okay, and it's mapped to set with additive. Well, the product is addition, right? And the mapping is very simple. F of an goes to n, simply n, right? The index here. So this element here. That this is a bijection is a trivial matter, and the reason is it is clearly invertible, right? For every n that you take here, every integer n, you can construct this matrix very easily. You just write the diagonal as once, 0 here, and then you put n here, and then you have constructed an. So it's very easy to invert. So this is trivially a bijection between the two groups. But that's not enough for this to be an isomorphism. For isomorphism, we need that the product is preserved. So we need to prove that this is equal to this, because that's the product in this group G, and this is the product in this group G, right? And these are the images of an and am. But that is also trivial, because if you multiply these matrices, right, if you multiply them, what you get is 1, m plus m, 1, 0. And therefore, the image of this matrix, which is the matrix, the product matrix, well, as a matter of fact, this is just this matrix. Well, the image of this matrix is just m plus m by definition. So yes, this is an isomorphism.